Differential calculus, special limits. Well, we all know that the first option is to substitute the value towards which the said variable is tending in, and hopefully it comes out with a number. So there are two examples of just that. Both of those come out with an acceptable number. Here a whole lot more. That comes out with 0 over pi, that one, which is quite acceptable, and that's equal to 0. So that one's fine. This one here has a bit of a problem because we end up with e to the 0, which is 1, over x, which is 0, so 1 over 0. So that actually we either say is there's no limit, or we can say the limit is infinity. The limit would of course be negative infinity if x is tending, if that is a left limit. So in other words, x is tending from the negative side to 0. And the next one, 0 over 0. Well, we've dealt with that before, and we know that we need to do further algebra. A non-zero over infinity. Well, any non-zero over infinity, if that number below gets big enough, we can get that as close as we like to 0. So therefore the limit is 0. And infinity over infinity, we actually need further algebra as well, exactly the same way as 0 over 0. So those two that require further algebra we call the indeterminate form, 0 over 0, infinity over infinity, where substitution does not give enough information to determine the limit. There are a number of other indeterminate forms. We're not going to deal with those though. We're just going to deal with the 0 over 0 and infinity over infinity. So let's look where x tends to infinity. Infinity is a concept, not a number. Note that. And it describes something without any bound or larger than any number. If x tends to infinity, you can give me any number and there are x's that are larger. So here's the first case. For n element of real numbers, n greater than 0, the limit of x to the n as x tends to infinity is infinity. Now x is getting very big, so you're getting a very big number, and that's the one that's changing. So no matter what this is, if it's a real number greater than 0, this is going to go towards infinity. And if x is tending to negative infinity, we're going to get it going towards negative infinity, though there is going to be a bit of a change here in that obviously we have to be careful here of even roots of negative numbers, and there's going to be alternating signs. So this one has a bit of question in it at times, needs to be evaluated further. No matter how large a given number k may be, the value of x to the n will eventually exceed k. That's the limit going to infinity. Why n element of r? Well, even something like a third, which is the cube root of x, that's also going to go to infinity. Why n greater than 0? Well, because n less than 0 will invert fractions and give a totally different case. Then, once again, for the same situation, the limit of 1 over x to the n as x tends to 0 from the positive side is infinity, and from the negative side is negative infinity, depending on the value of n. Because if n was an even number, then this would go to positive as well. So there are all sorts of extra provisos we need to add and conditions. But we're looking at it simply in this case. Then we have, for n element of natural numbers, 1 over x to the n as x tends to infinity is going to go towards 0. And as x tends to negative infinity, is also going to go towards 0, and that's this case here, becoming smaller and smaller. Let's have a look at some examples. So here's a case where the numerator is the same degree as the denominator. Here are two examples, degree 1, degree 1, degree 2, degree 2. So we're going to do a clever little trick. We're going to divide top and bottom by x, which is the highest power, the degree. We're allowed to do that because that's like dividing by x over x, which is dividing by 1. Separating those out and simplifying. Now I can distribute those limits. So the limit of 2 is 2 and the limit of 1 is 1 because they're constants. So we end up with these two limits there. And we've already established the limit of 5 over x as x tends to infinity is 0 and 3 over x the same. So therefore the limit is 2. We're going to do exactly the same thing with this one, other than the fact we're going to divide by x squared, being the degree of the numerator and denominator. These are going to go to 0. So we end up with 3 over 2. Now, if the numerator is a lower degree than the denominator, just one example, first degree, second degree, I'm going to divide by the highest power within the fraction, which is x squared. These are going to go towards 0. And that means 0 over 1, which means the limit is 0 as x tends to infinity. Numerator greater degree than denominator. So if x is tending to infinity, same process, dividing through by the highest power of x. We end up with that. Now this is getting bigger and bigger and bigger. So therefore overall we can argue that it's going to tend to infinity and that one's going to tend to negative infinity. Let's have a look at trigonometric limits. First of all, the straightforward values, y equals sine of x, so the limit of sine of x as x tends to negative pi is 0. You can see it from the graph. Negative pi by 2, the limit is negative 1. Those are all ones that can be determined by substitution, in fact, too. Cos has similar limits. And looking at tan, we have a difference because of those asymptotes. We have these asymptotes at negative pi by 2 and pi by 2. That's pretty straightforward. That one, tan is tending to infinity. As x tends to negative pi by 2 from the left limit. And of course the right limit is negative infinity. Left limit, once again, is infinity for pi by 2. Right limit, negative infinity. And we can see just straight from substitution, as x tends to pi, the limit is 0. Now there are two formulae we can use for evaluating trigonometric limits, right? The limit as theta tends to 0 of sine theta over theta is 1. That is proved by what is called the sandwich theorem, but we're not going to do it here. And the limit of 1 minus cos theta over theta as theta tends to 0 is 0. So that first one. Our theta here is 2x, so it's sine theta over theta, so it's straightforward, so it goes straight to 1. In this next case, we need to do a bit of adjustment first. So 3x cosec 3x, well, we can take the cosec 3x below to make it sine 3x, and this looks very similar to that. And in fact, this means that the limit of the reciprocal is also 1, because if you invert 1, you get 1. So therefore that has a limit of 1 as well. Sine 3x over 5x. These aren't quite matched, but we can go through a process to make them match. We just make it sine 3x over 3x and then say, what do we need to multiply by? So we've allowed for the fact that it is really still 5x. And there we are. 3's cancel and we still have the 5 below. So we can take that outside the limit, and the limit of sine 3x over 3x as x tends to 0 is 1, so we have 3/5. Sine 2 theta over theta cos theta. Well, we're going to have to establish this rule first, so I want to have sine theta over 2 theta, and we'll take the cos separately. First of all, I'm going to do it in a different way here. In fact, I'm using my double angle formula first, which simplifies to that, and that's very straightforward. But we could have done it the other way I'm talking about. Sine of 2 theta over 2 theta times 2 over cos theta is the same as the original. And that means limit of the left and limit of the right. And that one goes to 1, and this one goes to 2 over 1, because cos theta, if you substitute 0, you get 1. So the answer, 2. Sine 2 alpha over sine 3 alpha. Well, we're going to divide into two separate factors. There we are. Now that still is sine 2 alpha over sine 3 alpha. And so we know that that tends to 1 and that tends to 1, so we have our 2/3 as the answer. And tan x over x, we're going to convert tan x to sine over cos. Sine x over cos x times 1 over x for the division by x. Rearrange slightly, and there we have this rule again. And if we substitute 0 in there, very straightforward, 1. Now we can carry this out using LHospitals Rule. Some people say LHospitals Rule. Very useful for finding limits of indeterminate forms, of the form theta over theta and 0 over 0 and infinity over infinity. So what LHospitals Rule says is that if f of alpha equals g of alpha, and f of alpha and g of alpha exist, and g of alpha not equal to 0, then the limit of f of x over g of x equals the limit of f prime x over g prime x. So the limit of function over another is equal to the limit of the one derivative over the other. Let's take an example. There, we've done that already, but let's do it by using LHospitals Rule now. So we have our f of x, g of x. If we differentiate, that's differentiated using chain rule, we end up with cos of 0, which is 1. 1 minus cos x over sin x, there's our f of x and g of x. We differentiate. Remember that we are able to use the LHospitals rule because if I substitute 0 into there, I get 0 over 0, which is indeterminate. And therefore I can differentiate the top, differentiate the bottom. I get sine over cos and 0 over 1, which is 0. If we try that one, we get 0 over 0, indeterminate. So let's differentiate top and bottom. Now straight substitution gives us 3 minus 1, which is 2. In this case, we can do it another way by multiplying top and bottom by 1 root 1 plus x plus 1, and we can do it that way, but we can do it quite simply using LHospitals rule. That's indeterminate, you see, so it meets requirements for LHospitals rule. So therefore, there's f of x over g of x. I differentiate. Now when I substitute, all I've done is simplify at this stage because that becomes, goes into the denominator. I end up with a half. And here's another one case. -1. Here's an infinity case, x tending to infinity. Now this we did before, but we can do it more simply using LHospitals rule in this case. If we substitute infinity, we end up with infinity over infinity, so that is indeterminate. So therefore, I can use LHospitals rule, so I differentiate top and bottom. Now if I substitute, I'm going to end up with indeterminate again. So I'm going to differentiate top and bottom again, and now I can end up with 3. A very big beware of LHospitals rule. So therefore that shows the limit of f of x over g of x is 3. If I use LHospitals rule and say the limits, well, I'm going to differentiate 2x, differentiate 2x, I'm going to end up with 1. And that's not equal to the previous limit. Why is that? Quite simply because the limit of f of x over g of x as x tends to 0 is not indeterminate in this case. There we are. It's not indeterminate, which means that the LHospitals rule cannot be used. So this is what the big beware is about. Only use LHospitals rule with indeterminate forms.